individual error gradient. That means record by record, your weight update will happen. Whereas in the classical error gradient, what is the in this calculation, what we are going to do? Once I am going to present all my training records. This is a handover calculation, so I have only 3 training records. Suppose if you have 5,000 training records, once you presented the entire 5,000 training records, then only your weight updates happen. Then you represent the same 5,000 for the second time, second iteration. Then the weight update happens. Third time you present the entire 5,000. But here, once you presented the entire 5,000 record, you have to compute the total error gradient contributed by, okay, I index vary from 1 to 5,000. The error gradient contributed by the entire 5,000 record, because you are substituting the total error gradient. When I substitute the total error gradient in the formula, that is called as the classical gradient descent. Or one more terminology I'm introducing. So many terminologies you will be learning throughout this course. I just gave it as a jargon alert. Concepts are more important than I have seen. I have interviewed many candidates, many young data scientist candidates with the companies I work for, corporate training sessions, as well as the consultation work I do. I was part of the recruitment team. When we do the interview process, we have seen many youngsters, they just throw the jargons without knowing what is there inside the jargon. They think that if I tell so many jargons, we can easily impress the interviewer. That is not the case. You can use the jargons with the knowledge of the jargon. Otherwise, don't use it. If you're throwing a jargon, means naturally the interviewer will go deep, dig into that jargon, whatever you are using it. So without having a complete knowledge about the jargon, don't superficially throw that. And if you start to beat around the bush, and if you don't give a clear answer for that jargon, it will give a negative impact in the interview process. As much as possible, instead of throwing a jargon, try to explain the concept behind the jargon and then touch upon the jargon. That will be a very good interview strategy. In the first insight itself, don't throw the jargon. That is my point. Try to explain the concept with your own logical sense, with your own understanding. Then you link to the jargon. So what is the jargon alert? Here it's people call it this as a full batch training. Okay, this is called as a full batch training. Your full batch training substitute the total error gradient. Summation symbol. I use a summation symbol. But in the handover calculation, what we are going to use, it is not a full batch training. Okay. Sorry, we are following a full batch training. But another style is what? Record by record, the weight will update. First, they will present the first record. Immediately, then they update the weights. Then they present the second record. What is the error gradient contributed by the second record alone, they will consider, and the weight update will happen. What is the error gradient contributed by the third record, and then immediately weight will be updated. That style of learning is called as stochastic gradient descent. Stochastic gradient descent. Jargon alert, like a full batch learning, this is called as an online learning. Online learning. What is online learning process in ANN? Is nothing but record by record weight updates. Okay. The corresponding algorithm name is called as a stochastic gradient. Okay, this is the name of the application name. This is the theoretical name. Understand the difference. This is the theoretical name, and this is the application oriented. Similarly, what is the theoretical name for the full batch gradient? Full batch learning is an application name. Full batch learning. What is the theoretical name for this? Theoretical name is a classical gradient descent or simple gradient descent. If I don't use the term classical, by default it is understood as a gradient descent. Without the term stochastic, if people talking about a gradient descent means by default is considered as the classical gradient descent. That means we are substituting the total error gradient, not the individual error gradient. Okay. Towards the end of this calculation, I will also show you a snapshot of How do we perform stochastic gradient descent curves? Okay, we'll come to that shortly. First, let us try to finish this calculation. So I calculate the total error gradient to adjust the bias, calculate the total error gradient to adjust the slope. Okay, so we got this calculation. Now, how to substitute? For the substitution purpose, I need the learning rate, right? The learning rate for this handout calculation, I have taken 0.01. Okay. Once we finish this calculation, then I'll come to learning rate. We'll have a short discussion of this learning rate. What is the significance of choosing a very large learning rate or very small learning rate? So what is the optimal learning rate? How to start with the learning rate? Also, we are going to validate the learning, the calculations, whatever we are doing these calculations, we are going to validate with another set of Python notebook. So in this calculation, I have taken a learning rate value is 0.01. Now I need to update the bias. How do I update the bias? WB, okay, new, because I'm going to update the bias. The updated bias is equivalent to, what is the initial bias value is 1. Okay, so the general formula we kept as minus sign. Okay, already we substituted this minus sign here. Minus 0.01 times. Can you tell me what value I should substitute here? You can answer in the chat box. What value I should substitute here? Question mark. Very good. Excellent. 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 You are with me. So all of you are with me. Very good. So I need to substitute 13. Very good. 13. Okay. Now to update W1 new, because I have only one feature, so I call it as the W1, or simply you can call it W. So W1 new is my initially selected value is 3 minus 0.01 times. I should substitute 73. Now I'll get the updated bias, updated slope, right? In the next slide, I have these values. So the substitution, whatever the substitution, that substitution is done here. You could see what is the updated bias. Initially, we started randomly 1. It's got updated to 0.87. And initially, the slope we started with the 3. It got updated to 2.27. So you can see the step how I updated the bias and the weight. So weight and biases are updated. Now with the updated weight and bias, okay, now the model will check. Now how I am performing with the updated bias and weight. Am I performing good? Okay, with what motivation we have updated the bias and slope? With the motivation, with the scope of reducing the error. Okay, we need to cross check whether the error is reduced or not. So my y cap is nothing but net. It's nothing but 0.87 plus 2.27 times x. Okay, this is our equation. Now I plug in 2 here to see what is the y cap value. So when I plug in 2 in this equation, my y cap value is 5.4. Hope you remember your y cap for the randomly initialized value. Your earlier equation was 1 plus 3x, right? For the randomly initialized value, your first y cap value when x was 2, 7, right? So when x is presented as 2, model predicted earlier it's predicted 7, but actual is 5. Okay, the actual is 5. Now just we have done just one iteration. With one iteration itself, okay, can you see the value is approaching towards the actual? Earlier it was very far away from the actual 5. The difference is 2. Okay, but can you see the difference is reduced to 0.41? Now it is approaching towards the 5. Earlier, when x is 5, the model has predicted 16, right? With the updated slope and intercept, now it is going to predict 12.22. It's pretty closer to the actual. Earlier it was 16, very far away from the actual. Now I plug in 7 in the equation. Updated 7 I plug in here. Now I got 16.76. Okay, earlier this was 21 plus 1, 22, right? 22, far better than 22. Now 16.76. This is the individual error. Now I need to compute what is the total error. This is the individual error. 1 by 2 d minus o the whole square. The total error is 1.6562. So for the randomly initialize the weight and bias, hope you remember I just marked that the total SSE. Okay, we have marked that value somewhere 34.5, right, for the random initialization. With just one iteration itself, our error got reduced to 1.6562. So our error is reducing, going in the descending direction. That means whatever we have done, the adjustment will make sense. With just one iteration, I have to repeat this process. Now I'm going to proceed the same step for the second iteration. Remember, we are doing full batch training, right? That means a classical gradient descent. So once again, this is nothing but error gradient term to adjust the bias, error gradient term to adjust the slope. So I compute the total error gradient. Earlier, remember, this guy was 13. This guy was 73. Okay. Just before we update the weight and bias. This was 13, this is 73. With one iteration itself, can you see the total error gradient? 2.39 against 13. And similarly, earlier this was 73, now it is 14.24. This tells a beautiful story. What these two fellows are telling us, what these guys, these error gradients are trying to